Hi, everyone. I'm Michael. Today I'll present Sprints. It's a joint work with Lulu, Ittay, and Fan. Sprints is a new protocol that is based on the classical proof of work, but it provides a major advantage over proof of work by being 10 times less polluting, 15 times more energy efficient, and all of that while providing almost the same security guarantees as standard proof of work. So just quick background to what proof of work is. Proof of work is a consensus mechanism where miners or participants extend a data structure called the blockchain. They do it by solving computational puzzles. For this task, miners expend resources such as power and hardware, and they receive rewards in return. And that's what makes this game economically viable for the miners. The important takeaway for this lecture is that in order to attack the system, attacker must control the majority or more than 50% of the computational power in the system. And this is true when propagation delay is small enough. Why proof of work is still relevant today? Proof of work is truly decentralized in the sense that it requires no authorization for participation. Unlike other approaches where I need someone from the inside to bring me to the inside, in proof of work, I can just buy mining equipment, participate in the game, and exchange real-life resources for virtual assets. Additionally, if we follow the money, we can see that until this day, the majority of the market cap belongs to proof of work protocols such as Bitcoin. And Bitcoin is also the choice of most of financial institutions, such as ETFs and large firms. But as some of you may know, Bitcoin comes with a great challenge. In order to provide such vast security, it has to consume a lot of energy. And in fact, Bitcoin consumes more power than an entire large country like Argentina. And of course, high power consumption leads to CO2 emission. Also, Bitcoin creates burden on local power systems, like was the case in Sichuan, China, which led the Chinese government to ban crypto mining completely. The most notable alternative to proof of work protocols are a family of protocols called proof of stake. They're significantly more energy efficient, and usually they require stronger assumptions such as availability of nodes and existence of true source of randomness. Additionally, those protocols are less decentralized because they require existing participants to approve new ones. And the only way to enter the system is by buying coins from someone, and it must be through either centralized exchange or through peer-to-peer transactions, which are not decentralized. And finally, we have biasness in the initial coin distribution that are inherent to proof-of-stake protocols, which creates issues of fairness. A quick list of other alternatives are proof-of-storage protocols, such as Chia, that reduce the threshold for an attack to 27%. We have HAB that reduces the power consumption by 2 times, but also reduces the threshold for an attack by the same factor. And we have permission solutions such as Libra and Stellar that are completely centralized. So in this work, our goal is to design a new protocol that shares the good qualities of proof of work by being as decentralized and secure, but emits significantly less CO2 emission. So our protocol, Sprints, unlike Bitcoin, forces miners to mine intermittently. For example, they are forced to mine 5% of the time. By forcing them to mine only part of the time, we shift expenses from power consumption to hardware acquisition. And this is the important takeaway here. Sprints does not reduce the total expenses of miners. It only changes their profile. And by doing so, it reduces the CO2 emission per cost of attack, which is the right way to compare CO2 emission for different protocols. We can think of it intuitively as the CO2 emission per security unit that the system provides. And the way Sprints forces miners to mine part of the time is by introducing a new puzzle called proof of delay. Proof of delay is very much similar to VDF, and in fact, it shares the 2 requirements of VDF. The first is that it has to be sequentially computable, which, by the way, implies that the computational costs are negligible. Additionally, it has to be efficiently verifiable, like VDF. And finally, a new requirement here is that the computation time should be identical for all participants in the game. One way to implement it is to use VDFs and assume that weak players don't participate in the protocol, similar to how GPU miners or CPU miners don't participate anymore in the Bitcoin mining. There are other approaches for solutions in the community, but this is outside of the scope of this work. And through most of our work, we assume that we have a perfect proof of delay puzzle. So if we look at Sprint's timeline versus Bitcoin timeline, we can see that they are quite different. In Bitcoin, miners are forced to mine all the time or incentivized to mine all the time, meaning that they mine even when someone already found a new block, they immediately start mining the next block. On the other hand, in sprints, before calculating the proof of work puzzle, miners have to calculate the proof of delay puzzle, which, if we look at the macro, creates a situation where miners mine intermittently over time, and potentially they can mine only a small portion of their time. So one of the most important aspects of this work was to show that sprints indeed reduces the emission in the system. And the way we show it is by comparing sprints and Bitcoin. We assume that both systems have the same total reward R, and we consider economical equilibrium where miners' reward divided by cost equal to some M, which is the profit margin. We also consider two components for the cost, power, which is the OPEX, and hardware, which is the CAPEX. And our emission analysis includes both the CO2 emitted by the power consumption itself and by the emitted by the number of mining rigs. So if sprints increases mining rigs, and therefore their entire life cycle pollutes CO2, we want to include it in our analysis. So just a quick thought experiment that hopefully will help you understand the intuition behind the emission reduction in sprints. Let's assume we have an initial case where we have Bitcoin with total reward R, and the total expenses are R divided by M. There is some arbitrary division between power and hardware expenses. For the sake of example, let's assume it's 50%, 50-50. So when we transit to sprints and change the proof of work time to be 5%, what happens is that if we keep the total reward R, the total expenses are now reduced in the initial phase to be almost half of the original expenses, which creates economical opportunity. More miners enter the system, and after a while, the system reaches equilibrium, where the total expenses are again R divided by M. But now the hardware portion of the expenses is 95%, while the power is only 5%. And this is the essence of what sprints does behind the scenes. We use real-world numbers, and we get the following graph, that is the emission as a function of proof of work ratio, where proof of work ratio of 1 is just Bitcoin, where the emission is normalized 1. And we'll get back to this graph, but first few words about security proof. Sprints achieves persistence and progress, often called liveness, with the delta equals 0. We could not employ here existing proof methods from previous work because of the block creation in sprints being non-Markovian. We therefore developed a new proof methodology. And one of the surprising facts of our proof is that the miner gains nothing by conducting parallel mining, meaning that when they calculate the proof of delay of the next block, they gain nothing in terms of attack by employing their proof of work elsewhere in the chain. And this is the essence of why sprints is almost as secure as standard proof of work. One thing that we do have to consider here is the case when delta is greater than 0, and we then start experiencing forks. So the difference between sprints and Bitcoin is that if we assume the same interblock time for both protocols, the sprints proof of work time would be significantly smaller, which increases the chances that two miners would find block roughly at the same time, which what leads to blocks. This can make attackers' life easier and makes the system easier to attack. And we wanted to estimate this. What is the effect of this? We created implementation of sprints by forking a Bitcoin client. We created local network of 100 nodes connected with random topology. And we emulated realistic latency between those two nodes using OS tools. As for proof of delay, we used VDF construction by Veselovsky. And we also tweaked the difficulty adjustment mechanism to use second moments in order to estimate both the proof of delay and proof of work parts of the computation. So the main results of our paper can be seen in this graph. Basically, those are the results from before of emission per proof of work ratio, but now we also added the threshold for an attack as derived from our experiment. And we can see that there is some sweet spot here where we are at 5% mining rate, meaning that the proof of work is 5% from the entire block time. But the attacker threshold is very close to the original 50% and is 49. But the emission is reduced significantly by more than 10 times. So just to sum it up, Sprints is a hybrid proof of delay, proof of work protocol. It shifts costs from power consumption to hardware acquisition. It provides a major ecological benefit by reducing emission by more than 10 times. And all of that with slight reduction in security from 50% to 49%. Thank you very much.